Hello, Highlanders. So, 12.1, this lesson is all about limits. And the limit is sort of the predecessor to what you will do in calculus. The concept itself is something that only human mind can really think about. And so there's three things that we're going to look at in this section. Is when limits exist, when limits don't exist, and when the limit does exist, there's two different ways of looking at it. What's important to understand about a limit is that you can't have a limit unless you are approaching a value, and it's the same value when you approach it from the left and from the right. For example, let's say we have this line. Alright, so I'm just going to quick sketch. My y-intercept, I got a slope of 2. Okay. Now, there's a little misnomer out there, I'm sure, that you think limits are values that we approach but never get there. And yes, in some cases, that's true. In other cases, we can actually get there as long as it's the same y value. So when you think of limits, I really want you to think of y values because that's really what they are. You know, what are the y values that we are approaching? The dependent variable. In some cases, it might be an area. It might be a volume. It could be, just a random y value or a point. So when you think of limits, we're using x, just like if you think way back in chapter 2, I believe, when we were talking about where the function's increasing, where is it decreasing. And we used x values to decide where the function was increasing and where it was decreasing while we were looking at y values. Because, as the function itself was going up in y value, it was increasing. And then we used the x values to describe that interval. For example, if we had a parabola, kind of like this, and we know that we bottomed out at 0, 0, we would say that the function was increasing on the interval from 0 to infinity. We would say that it was decreasing on the interval from negative infinity to 0. So we were looking at y values to determine, well, limits are no different. We're going to look at the x values as we approach on intervals, and then we're going to see what is the y value that we have. So a notation might be, if I'm looking for the limit as x approaches on this particular function, let's say x approaches 1, right? And we have to look at it as we approach it from the right, and we have to look at it as we approach 1 from the left. And this is the function y. All right, so there's our limit notation. Just like we used asymptotes at times, we used end behavior. I mean, all of the limit notation that we've done with our work throughout the year, we're going to look at it here and to determine what is the limit. So, as we approach this x value from the right, remember the plus sign means from the right, so as we're approaching, what's y doing? What is the y value? And with some of these functions, we can just plug in 1 here, right? And we see that the value is 5. So if we plug 1 in, and we see that y is 5, now we got to look and see what is the limit as we approach the same x coordinate, but now from the left. So as we approach from the left, y is approaching 5 as well. So in this particular example, we see that we actually get to 5. right? It's not something, it's not a boundary wall that we're getting closer and closer and closer to, like when we did our geometric series. If you remember our infinite geometric series, when our R value was less than 1, we were approaching a value. If you remember that whole thing we did with fractions and how I showed you that 0.3 repeating has a limit of 1/3. Okay, that is one kind of a limit. This, again, is a limit that we actually reach. So I want to make sure that you guys understand that some limits are limits that we're approaching, and some limits we actually get to. Okay, so two different kinds of limits here. This is one that we actually get to. But what's important is that it has to be the same y value as we approach it from the right and from the left. It's got to be the same, or it's not. That's not a limit. For example, if I have something like this, right, and we look at the limit as x approaches 0. So the limit as x approaches 0, if we look at the graph of this thing, here's 0. Well, of course, we're undefined at 0, right? And again, remember, just because we're undefined doesn't mean that there's an asymptote there. It could be a hole, and holes are going to be really, really important for us. But as I approach 0 from the right-hand side, okay, what's happening? Well, this is the positive side of the x-axis, so these are all positive over positive, so like 2 over 2, 3 over 3, and they all reduce to 1. So it would be that particular type of graph with the hole there, right? So this would be 1. And then what happens as we approach 0? So the limit as x approaches 0 from the left, get your y, right? What's happening now? Well, the absolute value here, like when x is -5, is going to be positive 5 over -5, which is -1. So because these will always be negative on the negative side of the x-axis, the absolute value makes these all positive, so the ratio is going to be -1. So it's down here. Where this was 1, this was -1, and of course undefined here. So as we approach 0 from the right, we have a limit of 1, and as we approach 0 from the left, we have a limit of -1. Since these two limits are not the same number, we say the limit d and e, which is short for does not exist. So the limit does not exist. And for those of you kids out there that have seen Mean Girls, that was one of the big lines in that movie where she's sitting in her math class and she says, the limit does not exist. So anyway, that's the case here. So it's got to come to the same value. If it doesn't come to the same value, then we can say that the limit does not exist. All right. So, moving on. In the first section here, they use a lot of charts, and they want you to take a look at, different limits and seeing what those limits might be. So there's going to be some times when you're probably going to need to use your calculator. For example, let's say if we're trying to find the limit as x approaches 0 of x over the square root of x plus 4 minus 4. Okay, so in the first section they want you to use a table. In section 12.2 I will show you how we can go ahead and determine algebraically how to find that limit, if it does exist. So the goal here is, what happens when I plug in 0? And that's the very first thing you should do. Right? You're looking for the limit at 0, so plug in 0. If this were the limit as x approaches 2, plug in 2. One of three things is going to happen. Right? So what could happen? You could A, get a value, which is your limit. So when you plug in the x value you're approaching, or you're trying to look for the limit of, you plug in 0, this could happen. A, you could get a value, and that would be your limit, right? It might be a number, just like here. Right? If I took, because I was looking at approaching 1, I plug in 1, what did I get? My limit. Right? And again, based on the function itself, you need to make sure that you're approaching that same value from both the left and the right. That's critical, right? What happens when I plugged in 0 here? I get something that was undefined. So then we're just going to have to look at some values and approach that from both the left and the right. So in this particular example that I have here, I'm going to plug 0 in, and I'm going to get 0 over some number, which is 0. And again, I get 0. So what does that mean? That I get a value. If I look at this, and let's change this function to, leave that a 4 and make that a 2. What's going to happen when I plug 0 into here? I'm going to get 0 over 0. And 0 over 0 is what they call the indeterminate form. If I spell that right. Okay, but the indeterminate form is critical. That's the second thing that could happen when you get 0 over 0. Based on what we learned this year, that means there's a hole in the bucket. Right? That means we've got a hole in our graph. It's not asymptotic behavior. It's a hole. And that's good. That's a good thing. That means that if there's a hole there, there's a good chance that we have a limit. Right? If we remember back when we were doing our derivatives for the first time, way back in the beginning of the year, we were looking at those particular points on the graph to determine the slope of the tangent line, because we could find it when we used our definition of a derivative, which was the difference quotient, which we will be bringing back. All right, so in this case, when you get a 0 over 0, so like when I plug in 0, that's what I'm going to get here, is 0 over 0, which means it's undefined at that point, but it doesn't mean that there's not a limit. Right? So how do we determine? We have to make a table. So we make our table centered around 0. So again, we got to look at it coming from the left and from the right. So I'm going to go -3, -2, -1, 0, which we know is where the hole is. And then 1, 2, 3. And so I'm going to get out my calculator. And again, we can use the table function on our calculator to help us do this. So I got to go here, and I'm still in polar, so I got to change my mode. Get out of the light there. So I'm going to go to my mode, and I'm going to go back to functions. All right, so y equals, I'm going to type in the second one. Again, the top one, when we plugged it in, 0 over -2, the limit was just 0, and we could show that it's 0 coming from both the left and the right. So again, that's A, get a value. B, you get the indeterminate form, which is 0 over 0, which is what we're looking at right now. And then we'll come back and take a look at option C in a minute. Okay? So I'm typing in this function. So I've got x divided by parentheses, the square root of x plus 4, old calculator, minus 2. Alright, and then I'm going to go to my table, and I'm going to set my table to start at negative 3, which is what I have it on my paper here, and then I'm going to count up by ones, get my table values. Okay, so we see at negative 3 we're at 3. At negative 2 we're at 3.414. At negative 1 we're at 3.73. And then obviously 0 doesn't work. And then at 1 we're at 4.23. 4.44. And then scrolling down to get the third value, 4.6. So what we see, because from our table, is that we are approaching something right here, and then we are going away from it. So we are actually coming down this way and going up that way. So a guess, like if we were in class right now, I would have you take a look and say, what do you think this is? You know, where is the location of that hole? And you would probably say, looks like 4. Right? And so the way to find out would be, okay, well, can I get closer? And yes, you can. And this is where, get familiar with your graphing calculators. They are helpful. And so what we can do is go back to our table set, right where we started. And again, I'm going to go back to negative. Well, I'm going to actually start it at negative 1 because I'm going to change my delta table. And that delta table means what am I counting by? How much am I going up by each time? And if I want to get closer, if I want to close in on that 0, I'm going to put in 0.1. So now I'm counting by a tenth, which means I'm going to have a lot more accurate values. So if you see my table here, as I get closer and closer to that 0 value, 3.97, my error, 4.02. So you can see as I close in from the left, from the right to that 0, it looks like I'm approaching 4. And that is what it looks like to me. So based on this table of values, I would say that this limit is probably 4. And again, if you wanted to get even closer, I would start at negative 0.1 and then change this to 0.01, which is now, as we get even more accurate data, it sure as heck looks like it's approaching 4, right? So even though we can't just plug that in because it's 0 over 0, but it is approaching the same number from both the left and the right, so by definition, our limit is 4. So algebraically, how would we do this? Well, I will show you that in section 12.2, but for right now, you're using tables. So when you do your homework, use your graphing calculators. It'll save you a lot of time. Okay, so the third option up here, right? When we plug in the number, what else could we get? We could get some number over 0. So what happens if we get some number over 0? That is when we have that, remember there were two types of discontinuities. There were the removable, right, which is what this is. And then there was the essential. That's essential. Run out of room. So the removable discontinuity, in other words, that's where the hole is, right? The essential discontinuity means we couldn't get rid of it because it's not the 0 over 0. It's not the indeterminate form, right? If it's essential, that means we can't get rid of it. So what's there? An asymptote. And what we know about asymptotes is that we either go to positive infinity or negative infinity. right? So an example of option C, if we were to look at this particular function, its limit as x approaches 0 of 1 over x, right? Well, when we plug that in, what happens? We get a 1 over 0, which means it's not removable, it's essential. So we have an asymptote at x equals 0, and again, this is your hyperbola, right? But what happens when we approach asymptotes? We either go to positive infinity or we go to negative infinity. When that happens, the limit does not exist. So when you're approaching an asymptote, the limit does not exist. When you are approaching a hole, right, the limit does exist most of the time, right? I showed you two examples, one where it did and one where it didn't. And remember, we have to make sure that we understand that to be an overall limit, it has to approach the same value from the right and from the left. All right? And then here's an example where we don't have a hole or an asymptote. We're not dealing with anything in our denominator. We just have a y value for a given x value, right? And also a limit, right? As we approach 1, we get a limit of 5. As we approach 2, I mean, we could say, what is the limit as x approaches 2 of y? And again, plugging it in, what happens? We get a value. 2 times 2 is 4, plus 3 is 7. So there's, you're basically looking at y values at given x values. As you will see, as we go through chapter 12, this right here, the 0 over 0, the indeterminate form, that is the most important piece of information that we get, right? Because if we're going to start talking about derivatives, we know that my definition of a derivative, which is the limit as h goes to 0, right, of f of x plus h minus f of x over h, which again, that's just your slope formula, and we'll go through all that again, right? H, remember, is your change in x. So we're always going to have a hole here. Always, 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 right? So when we are able to find the limit as h goes to 0, then we're able to find that instantaneous rate of change because that's the slope formula. Right? This is our difference quotient. Right? And when we let the change in x go to 0, we're not looking at a slope of a secant line any longer. We're looking at the slope of the tangent line. And remember, the tangent line intersects the curve at one point, giving me the slope at a single point or an instantaneous rate of change, which is so necessary when you're looking at data. Looking for rates of increase, rates of decrease, and that is so important, like right now with this whole coronavirus thing going on, and they're looking at so many charts and so much data. As mathematicians, you guys should be looking at that data and determining the rates of change. And that's what they're doing. They're trying to figure out when is it safe. They're looking at mathematical modeling to determine if slowing the spread is helping or not helping. And of course it is helping. And we are going to, the next question is, when are they going to open up the economy? When it's safe. How do they know when it's safe? They're going to look at the numbers, and it's all mathematics, right? It's all determining the rate at which it's safe to go back into the workforce. And so even though it's scary times and weird times, I find it interesting from a mathematics standpoint, and you can see the power of mathematics in the real world. Okay, so again, this right here, the indeterminate form, that's what we're looking for. That's the whole deal. When we have a situation like this example we can do what are called one-sided limits. So an overall limit has to approach the same value from both sides, right? It's got to approach the same value from both sides to have an overall limit. However, some don't do that, like this one. And we could say, well, maybe it's important to just look at what's happening on the right side of this graph. In the real world, we might not have negative values for x. It could be a velocity. It could be an area, whatever. So we're only looking at this. So we don't really care about this. All we care about is this one-sided limit, what's happening when x is positive. And in that case, we would write it this way. That's a one-sided limit. That's also a one-sided limit. So overall, does the limit exist? No, because it's going to two different values. But we do have one-sided limits. And as you go through and look at your notes in your book, they'll talk about that a little bit more as well. Okay, so I just thought I'd do a couple examples. There's also, on page 855, there are some basic limits. There are some properties of limits. And the properties of limits are what are really important here. You have the limit as x approaches c of b times some function, which is equal to b times L, where L is the limit. So the idea is, if I have a function, f, where I can pull out a scalar, then the limit of that function times b is equal to the limit times b itself. Right? So it's almost like factoring that guy out of the function, finding the limit of f, which is L, and then you just multiply it by that scalar quantity. The limit as x approaches c, if we have a sum or difference. So f of x plus or minus g of x is equal to L plus or minus k. So in other words, if the limit of f is L and the limit of g is k, then we can do this separately. So if we got two entirely different functions and we want to find the limit of the sum, so the limit of the sum of the functions is equal to the sum of the limits. Or the limit of the difference of the functions is equal to the difference of the limits. Which again, if I can split these up because maybe they're just two entirely different functions, that's helpful, right? You can just find the two individual limits and either add them or subtract them depending on what it is you're doing. And the same thing is true for if this were a product or a quotient. That works, or even a power. Right? So you'll see that box. Make sure you look at that box on page 855. But the limit of the sum is equal to the sum of the limits. The limit of the product of two functions is equal to the product of the limits. The limit of the quotient is equal to the quotient of the limits, etc., etc., etc. And it works with powers. It works with roots. And down the road, you're going to see that that's also important, right? Because if we don't have to, let's say we got one big square root that we're trying to work with, maybe we're trying to minimize the distance. We're using the distance function, distance formula, right? That's got a big square root on it. We don't have to worry about the square root because we can just take the square root of the limit when we're done, which is kind of nice. Because when you're dealing with square roots and you're going through these methods of eliminating the whole, which we're going to show in 12.2, the easier we can make the function, the easier our life will be, which you will see. Okay, so make sure you look at that. All right, so a couple of examples. I'm going to go right to your homework here. So let's say we want to look at, we have f of x equals 7 over x minus 3. And we want to look at the limit as x approaches 3 of f of x. So, first step, right? Plug in 3. So when we plug in 3, what happens? We get 7 over 0, not 0 over 0. So what does that tell me about this particular question? There's an asymptote here, right? Since there's an asymptote, the limit does not exist, and we're done. Next example. Let's say my function is x squared minus 9 over x minus 3. And we want to look at the limit as x approaches 3 again of f of x. First step, plug in 3. Always just plug in the number, right? That's always what you want to do first. So what do we see here when we plug in 3? We get 9 minus 9 over 3 minus 3, which is 0 over 0. So when you get that indeterminate form, what does that mean for us? There's a hole. There's a hole. Which means we got to find the y value of the hole. That will be the limit. So how do we do that? Well, in this first section, you're going to set up a table, right? But we've done some work here in the past of eliminating holes. What we see on the top here is x plus 3, x minus 3 when we factor that binomial, and x minus 3, and then we can remove the hole, and what's left? That is the reduced version. And remember, when we reduce it, then we can plug 3 into here, and we can see that the y value at 3 would be 6. So 6, if we were actually to write in the whole location, it would be 3, 6. Which means, what's the limit as x approaches 3? It's 6. And we've done some of this, right? If you remember, back in the day. So the idea here is that's a method. That's an algebraic method. If we can factor and reduce the fraction, that's what we want to do. So 2 examples. One where we had an asymptote, therefore asymptotic behavior means no limit. Here we had a hole. When you have a hole, you have a limit. All right. Last example here. Let's say we got a piecewise function where it's negative 2x when x is less than or equal to 2, and x squared minus 4x plus 1 when x is greater than 2. And we want to find the limit when x approaches 2 of f of x. So, again, we're going to go ahead and we are going to plug it in, just like we always do. So we're going to take and plug in 2, and we're going to get negative 4. But we're also going to plug it in here too, right? So when I plug in negative 2 here, when I plug in 2, I get, on the top function, my y value is negative 4. When I plug 2 into here, I'm going to get 4 minus 8 plus 1, which is negative 3. So therefore, does the limit exist? And the answer is no, because we're not approaching the same value. And so when we're looking for the overall limit, we see that the limit does not exist there because, again, we're not approaching the same limiting value. could we look at a one-sided limit there? Yes, we could. And I'll show you that in 1 second here. Okay, so because these two are different at 2, right? When we're coming from the left, we're approaching -4. When we're coming from the right, we're approaching -3. Those are not equal, so the limit does not exist. If we were just looking at the limit as x approaches 2 from the right, that would be looking at this one, right? Because that's to the right, so coming from the right, what are we approaching? That answer would be -3. The limit as x approaches 2 from the left, that would be using this top one, would be -4. So these are what we call one-sided limits. However, the overall limit does not exist because these are not the same. So hopefully that helps you. So conditions, right? When the limit exists is when we hit a value. That is the same when you approach from the right and the left. Or you get the indeterminate form, which means there's a hole, and the y-coordinate of the hole is the limit. Or the limit does not exist when there's asymptotic behavior. The two y values are different when you approach from the left or the right. Or sometimes graphs oscillate, right? So as you approach a certain value in there, they just switch back and forth between like 1, -1, 1, -1, or something close together. But if they never approach the same value, if they're just oscillating all the time, then there's no limit, right? Because they're not the same. They don't follow that same rule. Okay, so that's pretty much everything in the first section. Again, as you're doing this and you're looking for limits, the first thing you want to do is plug in the value of x that you're approaching and to see what your situation is. It's going to be one of those 3 situations where you either have a value or you have the indeterminate form where you get 0 over 0, which means there's a hole. And in section 12.1, you're just going to go ahead and use a table, use your calculators to find the value that you're approaching. Or it's going to be something over 0 where it's asymptotic and no limit. Or you get something funky like this. Okay? And that is the end of section 12.1. So that should help you to get started on that homework. Mr. Lampkin out.